The density of a straight metal rod extending from the order triplet 0, 2, 0 to 0, 0, 2 is given by delta of x, y, z equals y plus z. Find the mass of this rod using the line integral of this scalar valued function. So to begin here, let's recall the definition for evaluating line integrals of scalar valued functions. So we can see that in order to evaluate this line integral, we need to find a parametric description for our curve C, and then use that parametric description to parameterize the density function, and then evaluate. So that's where we're going to begin. We need to find a parametric description for this curve, or for the straight metal rod. So we're going to use that description, this straight metal rod extending from the ordered triplet 0, 2, 0 to the ordered triplet 0, 0, 2 to help us find that parametric description. So if we have a straight metal rod extending from one point to the other, we can see that our parametric description is going to be defined as a line segment. And we can recall that a line segment can be parameterized by the vector valued equation of a line. So we have our vector r of t being equal to the position vector r naught plus t times vector v, our parallel vector. So this rod starts at the ordered pair 0, 2, 0. So that's going to be our initial point. We'll let p naught be equal to the ordered triplet 0, 2, 0, and we'll let our second point be p sub 1, 0, 0, 2. So our position vector, r naught, is the vector that starts at the origin and ends at the initial point p naught. So we can define this vector as the vector with components 0, 2, 0. And then to find our parallel vector, this vector parallel to the line segment, we need to find the components of the vector from our initial point p naught to the point p sub 1. So we have 0 minus 0 as our first component, we have 0 minus 2 as our second component, and then 2 minus 0 as our third component, leaving us with a vector 0, negative 2, 2. So we have everything that we need here to find the line segment, and we can say that vector r of t is equal to the position vector 0, 2, 0 plus that arbitrary parameter t multiplied by the vector parallel to the line 0, negative 2, 2. And we can simplify this so that we can see the x, y, and z components. So simplifying this line segment, we are left with the vector with components 0, 2 minus 2t, 2t. And this is such that t is greater than or equal to 0, less than or equal to 1. So this is the parametric description of the line segment that we are going to use to parameterize the density function. So let's recall that in this question we are given the density function delta of x, y, z is equal to y plus z. So we are now going to use the components of our parametric representation. So we have our x of t component, our y of t component, and our z of t component in this density function. So we can say that this becomes delta of x of t, y of t, z of t, and we're going to replace y with y of t and replace z with z of t. So plugging those components in, we have 2 minus 2t plus 2t. So we can see that those 2t's cancel each other right out, and we can say that our parameterized delta function is defined as 2. Beautiful. So the last thing that we need to do in order to set up this line integral is to find the magnitude of the tangent vector. So using the parametric description of our curve, or the metal rod, we can see that the tangent vector is the vector with components 0, negative 2, 2. And now finding the length of this tangent vector, we have that the magnitude of the tangent vector is equal to 0 plus negative 2 squared, which gives us 4, plus 2 squared, which gives us 4. So we have the square root of 8, which we, of course, can simplify to 2 times the square root of 2. Beautiful! So we officially have everything that we need now to set up and evaluate this line integral. So plugging in all the components we just found, we have the integral from 0 to 1 of the parameterized delta function, which we found to be 2, multiplied by the magnitude of the tangent vector, which we found to be 2 times the square root of 2, dt. So we can simplify this. That's the integral from 0 to 1 of 4 times the square root of 2 dt. And that's a cute general antiderivative. This becomes 4 times the square root of 2t from 0 to 1, which leaves us with a beautiful final answer of 4 times the square root of 2.